So what if this presentation is done remotely? What if actually what you see on the stage is not me in person? It's a hologram image of me. Is this science fiction? Probably not. So what I'm actually going to talk about is the transport network requirements and architecture for 5G. So the intro I gave you is kind of, probably sooner here than you can imagine, saying that, let me figure out how I actually move on this. Okay. So to kind of start to build a picture here, I'm going to start from what we have today, talking about 3G, 4G. I'm not going to spend a lot of time on this one. I just want to set the stage here for my next 30 minutes. So basically, what I'm going to talk about is why there are some key requirements for the transport network in 5G. And if we start to look at the 4G today, what you'll actually have is a few data centers. So looking at this from an architecture point of view, you see a lot of hardware. So ignore the details on this slide. My main point on this slide is that there's a lot of proprietary hardware software in this. Now, kind of looking at the next phase. So going from a few data centers into the 5G, where you actually start to see that there's a lot of micro data centers. So this goes actually pretty much back to Mike's presentation from Edge Micro yesterday, saying that there's going to be thousands of micro data centers. Guess what? This is actually the reality with 5G, and there's a reason for this. So reason truly being is that you go from a few cloud-based huge data centers into thousands of those. Now, to start to build the picture up here a bit, so why is that? Well, it's due to the fact that, I think it's easier to explain this to you if we pick an example. Many of you probably have heard of the, applications, use cases for 5G. So I'm picking one of them. Autonomous cars, self-driving cars. I guess, the majority of you guys heard about those ones, right? So to put this into some context, if you now compare that given use case in a 4G environment, what you're actually going to see is that assume that you actually have a car driving by itself in a 4G environment. The time it actually takes to get a response back, and then assuming you have your few cloud DCs, is about 80 milliseconds. That would actually mean that you talk about the car moving around 4 feet during that period of time of getting a response back. Okay, so now if we compare that to the 5G, saying that you now actually have your micro data centers, which basically means that your radio base station is truly close to your data center, to your micro data center. The same example, you can see that you have less than 5 milliseconds latency, which basically means that the car only moved like 4 inches. That amount of distance during the response I get back. So I guess, this starts to explain to us or build up the picture for us, saying that fact being is that we still need to have some kind of a network in place here. Now, would it be a small fabric somewhere? Would it be a huge fabric somewhere in your data center? It's still a core network. And the thing with 5G is that it's cloud native, which basically means that all the services are virtualized. So you basically start to look at, if you guys think of the RAN network today, the radio access network today, as I mentioned, it's a lot of hardware, software, proprietary. Now, it kind of have or from NFV, you actually start to look at all of these services, and you start to actually profile those being, why wouldn't we actually virtualize all of those ones? Putting those into the cloud. Now question becomes, would I have it in a big data center, in a micro data center? Everything is virtualized. So what I'm trying to make a point on here is that as 5G is cloud native, you still need to have a network in place. As you can see, you might have a network fabric, or you are going to have some kind of a network fabric. Now, question becomes that, okay, in a huge data center, I probably have a 3, 5, 7-stage closed fabric, while in a micro data center, I might have a small layer 2 fabric, for instance. So as we can see, there's different requirements based on actually where you are in the network. And that kind of goes back to what I was saying, that it depends on the different use cases you have, different applications you have with 5G. So I kind of picked one of those ones being, the smart vehicle. Obviously, there's other applications as well, use cases. I guess we don't even, we can't even imagine what use cases you're going to start to see with 5G. So there's a couple of ones mentioned here. You had a smart factory. You have IoT. IoT is pretty interesting, right? Because there was a survey done actually some time back saying that by 2024, that's like 5 years from now, you are going to have 16 billion IoT devices connected, out of which basically 4 billion is going to be mobile connected, the other ones is going to be wired connected. And then you start to look at the mobile and the mobile and the fixed broadband with 5G. So there's a lot of use cases, applications that goes with 5G. Media is an interesting one. Assume that you actually want to have 4K or 8K high-definition video on your handheld. That's going to put some demand on the bandwidth, right? And my point here is that you always basically go back to a network somewhere. It's all about connectivity. So to put it into some context, kind of again comparing the LTE and 5G. So as you can see, this goes into the latency. I think I kind of made my point already with the use case for the autonomous cars. But fact being is that you start to break up the network into different parts with 5G compared to the previous networks. And as I mentioned, my example for 4K, 8K video on your handheld, and this is, on a per device. So basically, you're going to see that there's a huge increase in bandwidth, and obviously latency being another thing here as well. And then you start to look at 1,000 times increase in the bandwidth per unit area, which means that you are starting to look at specific, antenna arrays, all that stuff. So building up the use cases again, and obviously we have mission critical services, being the public safety, for instance, where you today have your P25, your Tetra networks, and 5G would actually allow you to have things like push to talk. It would have things like sensors on vehicles. Basically, once you crash, you actually would send some kind of alarm on that one. So there's a lot of interesting applications around that one. You have the autonomous driving, as I mentioned, and then you go into Massive IoT, as I mentioned. You have your fixed and your mobile broadband. So this is just to give you a few examples of obvious use cases for 5G. Now, requirements. I've been kind of mentioning these requirements a couple of times already. But as we can see, it's obvious, you need to have 100% coverage. You need to have, low latency on those, and a huge increase in the bandwidth demand with my example on the media side. And then you go into, I said, the things like long lifetime of batteries on the IoT stuff, so on and so forth. I'm not going to dig into all those details. What basically, this slide shows you is obviously something I've been discussing already. Different applications, customer segments, the MNO business model, so on and so forth. So you guys have these as a reference, these slides. I'm not going to spend that much time on these slides. Now, what I want to spend some time on is actually the service enablers. So there's two there's two actually squares I want to kind of spend some more time on here. Ignore the four other ones now, it's more on the radio side, but the highlighted ones is network slicing and low latency networks. So network slicing is a pretty interesting one. So as I gave the example of self-driving cars, we understand that's a use case having specific requirements. So if you look at that one, you basically have the ultra-reliable low latency connection, being the example I gave you, which basically is going to be backhauled to a micro data center. And I kind of tried to build up the picture for us to realize why. Then you go into basically your mobile broadband, you go into the machine type communication, which might be backhauled all the way to the cloud data center somewhere with different requirements from that point of view. So the requirements kind of dictate how you're going to connect those. Network slicing is by the 3GPP defined as using the same network for multiple applications with different requirements. So somebody could ask then, okay, so define a network slice. What is a network slice? A network slice is a connection of some type. Basically, it could be a VLAN, it could be a VXLAN, tunnel. It could be basically anything. The key thing is that how would you fulfill the requirements from a network point of view for these given services? So as said, network slicing is something that is kind of a key thing within the 5G architectures. Now, low latency networks. So as we can understand, going back to my examples again, the different requirements are in regards to latency as well, which basically means that you could ask yourself the question, is TCP the optimal for that? Is TCP optimization something you want to do? Or is there some other protocols or mechanism in place? So there are some discussions of something called the ICN, which is one way of thinking of transporting traffic in 5G environments. So the topology. So I'm trying to get to my point here with the network part, truly explaining the network requirements. So 5G is all about softwarization of the network. As I mentioned, it's cloud native, which basically means that looking at the RAN, the radio access network, as I've been mentioning a couple of times, it's pretty much hardware software centric today with proprietary hardware and software. So if that actually moves into the C-RAN being the cloud RAN, or the virtualization of the RAN functions, which means that you basically have your radio tower and then you basically move all of your intelligence into your cloud, into your data center as virtualized. NFV and SDN, that's obviously a big part of the architecture itself, as we can understand. And obviously you start to have a network somewhere that is the transport for this one. You go into the MEC, which has been already kind of mentioned. So MEC is the mobile edge cloud, or it's the multi-access edge. So truly the edge cloud. And then you go into basically having your control plane and your data plane split up, basically decoupling those ones. So the network slicing part. This is the obviously from the network part. What you have is your orchestration layer, where you have your RAN orchestration, your core network orchestration, and your transport orchestration. Then you go into the different slices you have in the network. So you might have a specific slice for a specific enterprise. You might have multiple of those slices, so on and so forth. And then you go into all of your virtualized services within the network itself. And then the question becomes, okay, so if we talk about a huge amount of micro data centers, how am I going to actually orchestrate and automate all of this stuff? So I have different APIs for that, which basically means that you start to look at APIs for orchestrating all of this. So then you start to talk about something called the SON, which is, you know, a mechanism of actually orchestrating a lot of stuff and automating all that. You have different slices as mentioned. It's, you know, based on the application you have, based on the application requirements you have. And as said, you have your APIs, you have basically a way of interacting with those and automate and orchestrate all of that stuff. So the question becomes that 5G transport, is it more than a cost? So it's truly an investment for critical services. As I kind of tried to explain to you that there's going to be a lot of interesting use cases for this. And obviously it's an architecture as well that will obviously underpin the long-term development of 5G commercial offerings as well as use cases. And it's part of the universal edge. As I mentioned, you basically have your mobile edge, you have, you know, the packet, the optical coming together, you have your SDN, you have your orchestration layer, your different APIs, so on and so forth, automation. So this gives you an understanding of the, you know, 5G transport platforms. I think this actually example explains it better to you. So I'm going to skip the previous slide. But what this shows you is, you know, the network architecture itself. So a couple of key points I want to make here is looking at the 4G centralized RAN model. Obviously, as I kind of started my presentation saying, everything is around a few big data centers. While with 5G, you go into a distributed model with a lot of small micro data centers, which basically means that you go in a 5G, you know, architecture. You have your RU, which is your radio unit. You have your DU, which is your digital unit. You go into the CU, the customer unit. Now, the customer unit is actually an Ethernet switch, right? It's probably going to be a layer 2 switch. So going back to my example of your fabrics, this might be a small fabric in your edge network. And then you go into the backhaul, which is obviously your packet core. So looking at the obviously requirements from a latency point of view. Now, some key things I want to point out here. If you look at the left-hand side, what you see is actually the synchronization. So 4G actually uses GPS, while 5G is going to use PTP and sync key. PTP sync key, so that's pretty interesting due to the fact that, you know, you need to provide synchronization through your network. So what is, you know, the TSN, or as I mentioned, PTP, so time-sensitive networking. So obviously that's part of the 802.1q standard. It's the P part, the PTP part. So it's discussed as 1588 v2. So basically PTP is starting to gain more and more traction in multiple different industries. As you can see, like aerospace, automotive, media, which is pretty interesting that you actually go into PTP where you need sync. So there's a bunch of applications and use cases for that. And hence it's pretty interesting to actually see that that's a common kind of sync mechanism for the X-haul networks, being the backhaul, mid-haul, and the front-haul networks. So with that said, obviously TSN, I'm going to skip over this slide. It's for your reference. The only thing I want to point out on this slide is the, you know, if you look at the resource management, basically says that you're using something like the Yang data models. And this goes back to my example of, you know, the huge amount of micro data centers you're going to have in the 5G environment, which basically means that you need to have a truly scalable way of orchestrating and automating things. So this is basically just a recap saying that, you know, 5G model is, the 5G is model-driven automation. I kind of mentioned that already. So it's truly due to the fact that you have, you know, the edge cloud with a lot of micro data centers that you need to orchestrate and automate all that stuff. And part of, obviously, you know, the automation is based on netconf and young models, going away from the you know, CLI based and more moving into the API based. So what I like on this slide, I'm not going to go through this in details, but I, you know, want to point out the red square you have, which basically says that with the full mesh packet network architecture, cross-domain control will allow operators to support end-to-end services with the appropriate resources allocated in the radio core and transport. Cross-domain automation, which basically means that you're going to automate all the different factors within the network. PTP, this is not a deep dive on PTP, so basically PTP, what it's all about is a way of providing sync. What you'll have is some kind of a clock hierarchy, where you might have, you know, a peer-to-peer end-to-end clock hierarchy, where you have a grandmaster clock, and then you basically are going to synchronize your clocks in the devices based on this grandmaster clock. So this kind of just shows you a high-level overview of that one. This is a more in-depth slide for your reference, showing how you would correct, you know, your time once you pass through your network, different elements within your network. So there's multiple ways of doing this. As said, this is just a high-level picture of PTP, how it's done. This is basically a you know, blueprint for the 3GPP for 5G. And basically what I've been covering, you know, truly as a quick fly through is some of the requirement for the transport network within 5G. And what you can see here is obviously you have a separation of the control plane and the data plane. What I'd like to point out is that as 5G is basically going to virtualize all the services, you still need to have a transport network in place. You still need to provide connectivity on that one. As we saw, it's basically, you know, a huge increase in bandwidth requirements, and obviously you go into different latency things, how you would cope with those ones based on different synchronization mechanisms, so on and so forth. So I think I have 4 minutes to go. This basically concludes my presentation. And I'm going to be around here, so if you guys want to have a discussion, feel free to come on and fetch me and you know, have a discussion on this one. Obviously, you know, this is a pretty hard topic to cover in 30 minutes. So as said, this was a truly high-flying kind of walkthrough on this one. All right, thank you.
We got time for questions.
Questions? Yep.
Thanks. Dan McGray and Johns Hopkins APL. Just drilling down a little bit into your centralized versus distributed data centers. Right now, you know, under 4G LTE, there's eNodeBs all over the place, right? They're not centralized. On the other hand, the MME, you know, the subscriber database and all that, that can all be centralized. So in a way, you've got to break up right now into centralized versus distributed. I mean, you know, I get the point that you're making with the latency tax, but right now you've got a distributed model where some parts are all over the place and some parts are centralized. So that brings me to the question of like, okay, so what's all that different? Right now, you know, you can't, the RATCH can't take all that long, right? So it's, you know, I'm trying to figure out what the differences are actually going to be, because right now it's already sort of the way you're describing.
Yeah, I didn't really catch the question you had there. So the question was around the centralized versus the distributed?
It's already partially distributed and partially centralized.
Yeah.
You know, the subscriber database is centralized because that doesn't take very long. I mean, that doesn't happen very often, right? But the parts that, you know, the eNodeBs are already all over the place, right? So
agree, yeah.
Yeah, so you've already got a model where some parts are all over the place in 4G LTE. Some parts are all over the place and some parts are centralized. So it just seems like 5G is going to be a continuation of that, right?
Yeah, I agree, but I mean, then you go back to basically what I was trying to make a point on is depending on the application, your network slicing, which applications are kind of demanding specific or having specific requirements from your network point of view. And those might then actually use the micro data centers, which you then have as close to the tower as possible, compared to the other services that you then might have, the backhaul all the way to your cloud data center somewhere. So I think it's if you don't look kind of only on the radio part, I think if you start to look at, more from the application point of view, as said, everything is going to be cloud native, which means that all of the services are going to reside in the cloud. They might be distributed, they might be local, or they might be, somewhere as a basically application running in your cloud.
Right, it's just that when you distribute stuff all over the place, that's very expensive. So they're not going to do that except for things where they absolutely have to, the parts that really, really, really have to be out there on the close side, right?
Agree, yeah. Thank you. Any more questions?
Yeah. Tony Tauber, Comcast. I was kind of wondering with the network slicing, I mean, I agree with all the things that the previous questioner asked about, but where's the contention domain arbitrated? So like if you have the network slicing that happens in the DU or CU area, like the radio is all shared, right? I mean, do you imagine different terminals dedicated to different slices or applications, or does that?
Correct, but I mean, if you go back to my slide, basically saying that you have different slices for different applications. Application might actually be a mobile broadband. It might be fixed broadband. So it depends on actually what you have. Saying that, it doesn't really need to be everything mobile. It could be, a fixed service as well. I think the point I'm trying to make here is that you have a single infrastructure in place, but you need to share that infrastructure based on the use cases and applications. And then you go into the fact that you have different requirements for the applications. Assume you have a self-driving car competing with me using 4K video on my handheld. That's where the network slicing with how you're going to do it is an interesting question, so to say.
Okay, thanks.
Yeah, thanks. Any more questions?
Okay. Thank you, Michael.
Thank you.